Alright, welcome back, AP Calculus. We're going to finish lesson 3.1. So in section 3.1, we started talking about the idea of the definition of a derivative. And just to recap a couple things that we were looking at writing equations of lines. And to write the equation of line, we saw that you can use the limiting process to find the derivative. And what we're going to look at now in finishing up section 3.1, the idea of differentiability, having a derivative, having a slope, and how that impacts a function being continuous. So for example, if we look at this first graph, let's call this graph A. Here you have a continuous function. So from the left side, you could just follow the graph. There is this, what we call a cusp, kind of like a V-shape looking part of the graph. And that's a continuous function. So this is called the cusp. However, at the cusp, it is difficult to determine the derivative. So just because a function is continuous doesn't mean that the function has a derivative. So that's an important idea. Let's write that down. Just because a function is continuous that doesn't mean the function is differentiable. So if we look at graph B, this middle graph right here, along the graph, this function is continuous. But once you get closer to the red dot, that's undefined slope. That vertical part of the graph where the red dot is, that's an undefined slope. And then the graph, the slope turns positive again. The tangent line, so if I were to draw a tangent line, that would be a positive slope, then a less positive slope, eventually maybe the slope going towards a 0. But at the red line, at the red mark, there is a undefined slope at the red dot, undefined. So what we're saying is, you could have a continuous function, but your continuous function, there could be a moment on the graph, there could be a place on the graph where there is no derivative. The derivative is hard to determine. The derivative is undefined. And if you look at, okay, so that was graph B, the middle graph. I'm going to call that graph B. Let's look at our last graph, graph C. So clearly in this graph, you have an asymptote, meaning the blue parts of the graph doesn't, like the blue part of the graph going upwards towards the y-axis, it doesn't cross the y-axis. On the left side of the graph, same thing. It's like two different parts of the graph, but they don't cross the y-axis. So here we have a function that is not continuous, and we cannot even determine the derivative at x equals 0. So in graph C, if I were to write a little statement, I would say not continuous, and derivative. The derivative does not exist at x equals 0. We have an asymptote. We don't know what the derivative is at x equals 0. So again, we have in graph A and graph B continuous functions. However, just because a function is continuous doesn't mean that the derivative exists. There could be a place on the graph where the function is is not differentiable. Alright, so we have a different idea though. We have this theorem that says, well, if a function does have a derivative, if you could find the slope, if a function is differentiable, then that implies continuity. Then that means if your function is differentiable, then you have a continuous function. And so that's this theorem. If f is differentiable at x equals c, then f is continuous at x equals c. And we're going to look at some examples of what we mean by this. Warning, the converse of the above statement is not true, and we saw that earlier with some of the previous examples. So let's look at the absolute value function. Let's look at that example, absolute value of x. And I'm going to draw this kind of graph to my best of my ability here. And we're graphing the absolute value of x, which is a V-looking shape. That's the graph of the absolute value. So here we have a continuous function. It's a continuous graph. The question is this graph differentiable? So from the left side of the graph, right? If I'm on the left side, this light blue part, we know what the slope is of that line. The slope of that line is -1. So I'm just going to mark that here for you in red. Here, the slope is -1. Now, if we look on the right side of the graph, I'm going to highlight that in yellow. Highlight that in yellow. Nope, that's not yellow. Highlight in yellow. Okay, there it is. So on the right side of the graph, okay, this has a slope of +1. In other words, on the right side of the graph, that equation is y equals 1x plus 0. On the left side of the graph, the equation is y equals -1x plus 0. Clearly we have two different slopes. Two different slopes on the left side of the graph. On the right side, one of the slopes is -1. The other slope, the yellow part of the graph, is +1. So the issue comes about if you wanted to find the derivative at 0, at the origin. At the origin, is the slope -1 or is it 1? And that's the question. Just because a function is continuous doesn't mean the function is differentiable. And you see that in this example in the absolute value function. So let's just write a note of what we're saying here. We're saying the absolute value function is continuous at x equals 0, but not differentiable. We cannot determine what the slope is at x equals 0. And this particular example, this is called a corner. Not differentiable. This is called a corner. So we cannot find the derivatives at corners. I'm going to go back to graph A. We cannot find derivatives at cusps. We cannot find derivatives at undefined slopes. And similarly, we cannot find the derivative of an undefined slope. And that's what that dotted red line was. That was an undefined. That was an asymptote. Undefined. At asymptote. At the asymptote. Alright. So back to our example. Let's look at our next example. You have this piecewise function. Let f of x equals 4x squared when x is greater than or equal to 1. Or we have a different graph, x plus 3 when x is less than 1. So there's two parts to the graph. We have a quadratic when x is greater than 1, greater than or equal to 1, and we have a linear graph when x is less than 1. So the first question, part A, is, do we have a continuous function? Is f continuous? Now, there's a little checklist that we have to do, and we've talked about this in a previous lesson. So the first check to determine if a function is continuous, I'm just going to put like a little star here. You got to check the connections. And the connections that we're talking about is these values at 1. That's the connector right there at 1. So you got to check the connection. To determine if a function is continuous, there's 3 things that we got to do. So step 1, does the value exist at 1? Does f of 1 exist? So look at your piecewise function. The part that says x equals 1, that's this guy right here. And that's 4x squared. So you're gonna plug in 1. Plug in 1 into x. Plug in 1 into 4x squared. So if I plug in 1 into 4x squared, because that's where x is equal to 1, f of 1, 4, plug in 1 wherever you see a x. And we're only using the top piece of the function because that's according to the inequality, x is greater than or equal to 1. So we're just using the top part, plugging in 1, and you get 4. So the function is defined, f of 1 does exist, the function is defined at 1, and you get 4. Check number 2. Does the limit exist? Does the limit, let me fix that, I'm sorry. Fix this little writing right here. The question is, does the limit as x approaches, we're checking our connections. As x approaches 1, does the limit exist? And in order to check the limit, you have to check 2 parts to this. So there's going to be 2 components. Do this. You got to check the limit from the left. As x approaches 1, from the left side of f of x, is that the same as the limit of your function as x approaches 1 from the right? So you got to check both parts. Alright, so what's to the left of 1? To the left of 1, that's the less than. So this is the part that we're going to use. That's to the left of 1. X less than 1. We're going to plug in x plus 3. That's our function. So we have the limit. X approaches 1 from the left. The function, one more time, is x plus 3 equals, and we're not sure, we got to check to see if they're equal to each other. The limit as x approaches 1 from the right, the other function is 4x squared, because we're approaching 1 from the right side. 4x squared. Alright, so we gotta, at this point you could just do plug and chug, plug in 1, since that is possible, and you get 1 plus 3 on the left. On the right side you get 4 times 1 squared. In other words, 4 is equal to 4. Check, the limit does exist. And since we're checking continuity, there's one more condition that you have to check, and that's number 3. Is the function defined, in this case f of 1, is that the same as the limit as x approaches 1 of your function? Well, f of 1, that was step number 1. That result was 4, and that's the same as the limit. The limit was also 4. So those are the 3 checks. That's our checklist for continuity. Remember our checklist. You gotta check if the function exists. You gotta check if the limit exists. And the third check is, does the function value equal to the limit? And that's how you check for continuity. So this is checking for continuity. Alright, for part B, is f differentiable at x equals 1? So this is new for us now. We got to check differentiability. And so what's the game plan? What's our new checklist? Well, for this game plan, put a little star right here. We got to check derivatives from the left and right. We want to make sure that the slopes are the same, that the derivative from the left part of the graph is the same as the right part of the graph. So, check derivatives from left and right, and if they match, f is differentiable. Okay, f is differentiable. So we have to figure out what are the derivatives from the left and what's the derivative from the right. So let's do this. Derivative from the left. Let's look at, let's just write derivative from the right since we're writing derivative from the right. So let's look at our function from the left side. As we are approaching 1 from the left side, that's this function here. This is the left side. Left. And from the right side, anything to the right of 1, that's the top function in yellow. So from the left, if I need to find the derivative, we're going to use that limiting process. Do you remember that? The limit as x approaches 1. And the formula is f of x minus f of 1. We're using the alternate definition of derivative formula because we want to find the limit at 1. So this is the alternate definition of derivative. And this is going to give us the answer for f prime, the derivative, at 1. So then, since we're using the derivative from the left, f of x is x plus 3. That's our function. So the limit as x approaches 1 of x plus 3 minus f of 1. F of 1, we found that to be 4 earlier. Subtract x minus 1. At this point, you can simplify. X minus 1 over x minus 1. The limit as x approaches 1. You could cancel those terms out. Cancel the x minus 1 and the x minus 1, and you get 1. So this becomes 1. That's the derivative from the left. Is that the same, question mark, as a derivative from the right? So now from the right side, we'll do the same idea. We want to find the derivative at 1, but this time we're using the right side. We're using the equation, which is the top part of the equation, 4x squared. 4x squared, that's the equation from the right. So instead of, let's write our formula, f of x minus f of 1 over x minus 1. That's the alternate definition of derivative again. F prime of 1, that's a derivative at 1. We're going to use the 4x squared. F of 1 is 4 over x minus 1. We can go ahead and factor out the 4's. and you get x squared minus 1 over x minus 1. Then at this point we can factor some more. The top becomes x minus 1, x plus 1. It's a difference of squares. You could cancel out the x minus 1s. Then you could do plug and chug. Wherever you see an x, plug in 1. So you end up with 4, 1 plus 1, which is 2. 4 times 2, which is 8. 8 is not the same derivative as 1. The derivatives are different. So the conclusion, since the derivatives are different, f is not differentiable. At x equals 1. We were checking the connection at 1. We know the function is continuous, but the derivatives are not the same, so the function is not differentiable at 1 because the derivatives from the left and right do not match. Alright, and so that's it for this 3.1 lesson. When we're checking if a function is differentiable, you gotta make sure that you check the derivatives from the left and right. How do you check derivatives? Remember that limiting process, finding the limit. And there's two formulas that we can use. What I was using here was the alternate definition of derivative. Alternate definition of derivative. But you have options. You can use the normal definition of derivative, if you like, which is f of x plus h minus f of x all over h, the limit as h goes to 0. So that's another. That's the normal definition of derivative. But we were using the alternate form because we were trying to find the value at 1, and we knew what f of 1 was. We found that f of 1 was 4. There's our 4 right there. And so that's what we were using. So when you want to check derivatives, again, use the limiting process. Check to see if the derivatives are the same. In this case, the derivatives were not the same, so f is not differentiable. And that's it. Thank you guys for checking in. We'll go over homework. We'll go over any questions you might have in class. Take care.